learned a lot of stuff. We learned about ions, the common ions that are formed by some of our favorite elements, our main group elements. We also talked about our transition metal elements. Reminder that our transition elements are in that little mini, the rectangle in the middle, and our main group elements are on the first 2 columns and the last 6 columns. And those ones are nice and repeatable, and also nice and repeatable in terms of charge. And we also know that zinc and silver also form the same charge every single time. Our transition metal elements are a little bit more wily. They can usually form multiple types of cations, and that's what we're going to be starting off with today. So especially if we're starting with a chemical formula, it's not immediately obvious to us yet what the charge is on that cation, the positively charged ion or transition metal element. And so we need to do a little bit of algebra to figure it out. So we need to first determine the charge on the anion that's negatively charged. So that could be things in our 5A, 6A, or 7A groups, or it could be a polyatomic ion group that we find on our green sheet, or that we're given in some other way. And we know that the sum of the charges must be 0. Otherwise, we wouldn't get a neutral formula unit. Reminder that our formula unit is just the chemical formula. It's the simplest whole number ratio of these subscripts. So if you had, for example, if we had 2 and 4 here somehow, we would have to simplify that down to 2 or 1 and 2. 2 and 3 works though. We can't simplify those numbers anymore. So if we're looking for the charge on Fe, that's iron, in this compound, Fe2O3, the first thing we want to do is figure out what's the charge on oxygen. Oxygen always has the same charge. We look at our periodic table. It's in the group 16 or 6A column. That means if it was an ion, it would still have 8 protons, but it would have 10 electrons. So it would have an overall 2 negative charge because there's an excess of 2 electrons. So this would be O2 minus if it were an ion. And we have 3 of them. So 3 times 2 minus, that's going to be an overall 6 minus charge. This whole thing, this whole formula unit, has to be neutral. And so both of our ions together have to have a 6 negative charge, or a 6 positive charge, sorry. So we have a 6 positive to balance the 6 negative charge from oxygen. And we have 2 of those irons, 2 of those Fe's. So our charge has to be what? 3. We need to have a charge of 3 on our irons. So this is iron 3+. Some of you might have noticed that the subscript of the oxygen is 3, and the charge of our iron ended up being 3. Maybe we can do a reverse crisscross method to get the charge on our cation. That will work sometimes, which is why it's dangerous. It doesn't work all the time. In this case, it works out okay because the subscript of our iron is 2, and we know that the charge of our oxygen is 2, so in this case, it will work out. Other times, it will not work out. So I don't recommend just trying to do a reverse crisscross method to get the charges, though it will work sometimes. So use that shortcut if you would like to at your own discretion. Okay, so we've learned how to figure out the charges on things that can form multiple cations. And we learned last time our naming convention for ionic compounds. Does anyone remember what that was? Some ideas about it?
Negative. It ends with an ID.
Yeah, so we're going to have name of cation. That's the positively charged one, or the metal, usually a metal. And name of anion. And our anions, if it's monoatomic, if it's just one thing, that means it'll end in "ide." So if it's monoatomic for our anion, it'll end in IDE. If it's a polyatomic ion, it's just the name of the polyatomic ion. So we're literally just naming the two things that show up in our ionic compound. And if we're doing something that has options, like lead can form multiple types of cations because of where it is. So we also have to include in the name the ion charge. So let me take another example. Let's say that we have chromium. Chromium forms a couple of options. One of them is 6+, hexavalent chromium. It's bad for you if you breathe it in. So we have to write, since it can also form trivalent chromium, which is a trace nutrient, which is good for you, we have to specify that we're talking about chromium 6. That makes a difference if we're trying to go back to a chemical formula from the name. So the idea behind the nomenclature is we can have the name, we can work back to the formula, or we can have the formula and work to the name, and there's only one possible option for both of those. We can't say a name and then come up with two different things. There's only one route. But that also means that we've got lots of little rules to follow. Okay, so in the compound PbO, the first thing we want to do is remind ourselves what the charge of oxygen is. If oxygen's an ion, it's O2- because it's in the 6A column like we talked about before. Step 2, the charges need to cancel. We need to have a neutral formula unit. Since we just have one of each thing, hopefully you can see, maybe you can see, that our lead then is just going to be a 2 positive charge to balance out. So we've got oxygen that's a 2-. We've got one lead. To balance it out, that'll have to be lead 2+. So then we would write out the name, lead, parentheses 2 in Roman numerals, the base for oxygen, which is ox, and then end it in IDE. So lead 2 oxide. Once you get really practiced at this, you can just look at the chemical formula and read it off, even if it's got multiple charge options. It's kind of fun. It's a flex that has no importance whatsoever in most contexts. Okay, so now try naming this compound that's made of copper, Cu, and sulfur, S. Okay. Naming the compound Cu2S, we need to figure out the charge on our sulfur. Our sulfur is just below oxygen. It's going to have the same charge, so it's going to be sulfur 2 minus. That would be the sulfide ion, or just sulfide. The copper has to have a charge that balances out the 2 minus. So it's going to have a 2 positive overall charge split between 2 coppers. So those twos are related, and then this X is the charge on copper. Hopefully you can see the X is going to be a 1. 2 times 1 is 2. So copper plus, or copper 1. So this would be the copper 1 ion. And then our name for Cu2S, copper, and then in parentheses the letter I, the Roman numeral 1. The start of sulfur, sulf, and then change the ending to IDE. So copper 1 sulfide. Questions about this very thrilling nomenclature? Yes? The overall charge for a formula unit will always be neutral. All right, we also have oxyanions. Oxyanions are one of our big classes of polyatomic anions. You can find a bunch of the oxyanions that we'll use in this class on your green sheet. It should be up in the top section, and you may notice that the way that the names, the elements in those boxes are ordered is the same as we see on our periodic table. So all the way in the far top left, you should see borate. Then next to it, carbonate, nitrate, and so on, for all of the oxyanions that we are going to use. And oxyanions contain a series, so there's a couple for each of them, and the naming is different for each of those. It's a systematic naming, so you have to memorize one or look up one and then know how to change the name to get to the other ones. If you're going to memorize one, you should memorize the one that ends in ATE. So for example, CO3, 2 minus, you might write on one side of a flashcard and then on the other side, carbonate. And you would just do that for all of those. There's a couple that are ones that I would recommend memorizing. You'll need them later. Carbonate, nitrate, phosphate, sulfate, chlorate. Those are the ones that you'll probably have to have memorized. I think I make you memorize those by the end of the class. So the oxyanions with those would be the ones to memorize, because those are the ones we use the most. So for CO3 2 minus, that's carbonate. If we have the oxyanion in that series, so still carbon, but we take away one oxygen. So CO3 2 minus is our carbonate. If we take away one oxygen, CO2, the charge is still 2 minus. In a series of oxyanions, the charge is always the same. Then this would be carbon, but we change the ending to ITE. And you might remember that because a light, quote unquote, light drink, LITE drink, is going to have fewer calories. Like Bud Light as opposed to Bud Heavy. Other examples include nitrate. the ATE ending, this is the one that you'd find on your oxyanion table, NO3 minus nitrate. If you take one oxygen off, now you're NO2, still 1 minus, and we've changed the ending to ITE. So 8, and then just below it, ite. So we've subtracted 1 oxygen to get to the ITE form. And again, charge is the same, but only within a series of oxyanions. So like if you look at nitrate versus sulfate, nitrate is NO3 minus. It's got the 8 ending. Sulfate is SO4 2 minus. It also has the 8 ending. They have different numbers of oxygens. They have different charges. Not that they're all like unique configurations of those, but there's not like we can just memorize that the 8 form has a 2 minus charge or it has a certain number of oxygens. Unfortunately, it doesn't work out that way. Questions so far about our oxyanions? All right, I'm having the most fun, apparently, it looks like, in the class. That's okay. That's typical. We can also have series where we expand. So we've got our 8 ending. Right, that's the one you'd memorize or look up. We've got our ite ending, subtract 1 oxygen. And then we have options for adding and subtracting even 1 more. So our adding 1 more option, we add this per to the front, P-E-R, like in hyper. Like hyperactive, you're more active. Hyperchlorate or perchlorate, we've added 1 oxygen. Notice that we still have a 1 minus charge. The charge has not changed across our series. And we also have our minus 2 oxygen option, where we add a hypo, and we still have the ite ending. So we've got 8 and ite in the middle. If you add 1 to the 8, you add the per prefix. If you take 1 off from the ite, you add the hypo prefix. So they're kind of like additive effects. We've changed the ending to subtract 1. We've also added the prefix to subtract another 1. Hypo, like in hypoallergenic, which is supposed to produce less allergens and cause less allergic reactions. You also have a table on your green sheet that has these rules on it in reference to the 8 endings. So combine the oxyanion table at the top and the little table to do this stuff, and you can come up with all of our oxyanion options. All right, we want to name some ionic compounds that contain oxyanions. First, let's name the compound CrCO22. Just like with our other examples, the ones we started with, we need to figure out the charge of our anion first. So we would look at our table, and we would find the oxyanion with carbon in it. What do we find when we look for that? What's the chemical formula for that oxyanion? Yeah, it's CO3 2 minus, and the name is carbonate. Do we have CO3 in our equation? we have CO2, and that's one less oxygen. So CO sub 2, still 2 minus. We lost one. It's a little bit less oxygenated. It's our light form. It's our carbonite. So our anion is carbonite. And we have two of them. Times the 2 minus charge. We have an overall 4 minus charge from our carbonites. We can then use that to figure out the charge of our chromium. We have one chromium. It must have a 4 positive charge to balance out the 4 minus. And we can put the whole name together. So our metal is chromium. Chromium can form multiple charges, as we saw earlier. So we need to specify what charge the chromium has. In this case, it's chromium 4, so chromium IV. And our anion is carbonite. Questions about those steps? How we came up with that formula? How we came up with the name, rather? Yes? So a couple steps, right? We need to figure out the name of our cation, our positively charged one. That's our chromium, our Cr. So we'd find it on our periodic table, probably our yellow sheet. It tells us it's chromium if we don't have it memorized. So we're going to be starting with chromium. Chromium lives in our transition metals block. Right, it's in our transition metal block. It's not zinc or silver, so we don't know exactly what charge it is every time. So we're going to have to sleuth our way to figure out what that charge is. In order to do that, we need to know what the anion charge is. So we would find our anion. In this case, it's the CO2. We're only doing binary ionic compounds. So CO2 together, that's our anion. We'd find the thing that looks like CO2 on the top of our green sheet. The thing that we find that's close to that is CO3 2 minus, carbonate. We have CO2. It's still going to have a 2 minus because it's in the same series. It's the same nonmetal plus oxyanion, or plus oxygen. So it's still going to be a 2 minus, but it's CO2. So CO2, 2 minus. Since we dropped one of our oxygens, the 8 ending turns into the ite ending. So now we have the name and the charge of our anion, and then we can figure out through some simple algebra what our charge on our chromium is going to be, and we plug in those changes as the Roman numerals for the charge, the ite ending for our oxyanion. Again, once you get really good at this, you can do it almost instantly, but it takes a lot of practice to get there. It should get easier the more that we do it. And there's questions that are in the homework that cover this stuff. If you've got questions, you can come to office hours. I'm thinking I'll probably move my Wednesday office hours to be down in the math center. So look for an announcement about that. Now, you've seen it in action. Give this naming a try, CONO3. See if you can sleuth out the name of that. All right, CONO3. First thing we want to do, there's a couple options, but we might start with figuring out what CO is. CO is cobalt. Cobalt lives in our transition metals block, so we don't know what the charge is. It could form a couple of different options at least. So we'll have to figure out what the charge is. That means we need to look at our anion. NO3, we'd look at our green sheet, we'd figure out that's nitrate. The charge on nitrate is 1 minus. We've got one nitrate group, we've got one cobalt group. So if we've got a 1 minus on our anion, our cation has to be a 1 plus. Right, 1 plus, so we put in our Roman numeral 1. So cobalt 1 nitrate. The first time that we encounter all of this naming stuff, you'll be given a bunch of stuff on the greet sheet. You don't have to have the anions memorized. You should have some of them memorized, as mentioned previously, kind of towards the end of the course. So that wraps up naming ionic compounds. That's our first group of compounds. We also have molecular compounds. Arguably, molecular compounds are the easiest. For molecular compounds, in order to name something like a molecular compound, we need to identify that it is a molecular compound. Molecular compounds contain 2 or more nonmetals. We're going to only be naming binary or 2-element molecular compounds. We are only going to have nonmetals in molecular compounds. Our naming convention, super straightforward. We have prefixes. These are the first 10 prefixes. They can get much higher. We're not going to go past 10 for the most part. So our prefixes, mono refers to 1, di for 2, tri for 3, tetra for 4, penta for 5. Most people usually pretty good about those. Hexa has an X in it, just like 6. Hepta is a weird one for most people. Then we've got octa, like octopus. Octopuses have 8 legs. The octagon has 8 sides. Nona is another weird one. And then deca, like in decade, 10 years. So the ones that I've circled, those are just the weird ones that I expect that you're probably going to have the most trouble with. Maybe the N in Nana, N like 9. So these are all of our prefixes. You can also, keep counting up. There's nomenclature for going into the hundreds. We're not going to go there. For naming our molecular compounds, we've got binary systems, binary molecular compounds. So we've got 2 elements. If our first element has just 1, then we omit the mono. That's our one weird rule. Omit mono for the first element. Just for the first element. If we have a mono for our second element, we don't omit that one. So for example, CO2, we've got 1 carbon, 2 oxygens. Since we've got 1 carbon, we would put a mono. The rule is to omit that, so it's just carbon. We've got our oxygen up next, 2 of them. So we use our prefix for 2, which is di, di. Then we have the base, ox, from oxygen, and we also change the ending to IDE. There are also some cases, you won't get marked points off if you don't get this perfectly right. There are cases where, like in N2O, oxygen starts with an O. The mono prefix that goes in front of it also ends with an O. So we would shorten this to monoxide instead of monooxide. If you write monooxide in this class, that's fine, I'll just make a note, but you won't lose points for it. These are both fine. Any chemist that reads it should know what you're talking about. They might be a little grumpy and stodgy, but that's their fault. So naming molecular compounds. The compound N2O4. We need our prefixes for 2 and 4. Our prefix for 2 is di, and the name of the element N is nitrogen, so dinitrogen. And then we need our prefix for 4, tetra. So dinitrogen, tetra, the base for O, which is ox, and we change the ending to IDE. So you would probably come up with dinitrogen tetraoxide. Usually that would be dinitrogen tetroxide. So we might drop the A on the tetra. Questions about coming up with that? Quite a bit easier than ionic compounds, arguably. We can also do the name for the compound NH3. There's a common name for this one, but we're going to come up with the systematic name. How many nitrogens do we have? 1 nitrogen. We have 1 nitrogen. That's our first element, so we're going to omit the mono. So mononitrogen, just nitrogen. What's our prefix for 3? Tri, like Triforce. And then our base name for H is what? Hydrogen. So we take off the ogen part, hydr, and end it with IDE. So nitrogen trihydride.
Is that ammonia?
That is ammonia, yes. Ammonia is the common name. Yes. The "ide" is part of the naming convention. So whatever our last one is, we'll just change the ending to "ide." All molecular compounds in this class that are binary, yes. That's kind of all there is to it for molecular compounds. Our last group, we've now covered ionic compounds, things that are metal and nonmetal. Our second group that we just covered is nonmetals only, molecular compounds. Our third group is acids. Acids are molecular compounds because they're just made up of nonmetals, and they form ions when they dissolve in water. The fastest way to identify an acid, at least in this class, is that hydrogen is the first element in the formula. Anytime that you see an H or multiple H's in front, that means that you're dealing with an acid for this class. Some things that we call acids won't have an H in front in the real world. Those are beyond the scope of this class. Take organic chemistry if you want to learn about those. So our acids we're going to categorize into two groups. The reason that we categorize it into two groups is because we have two different naming conventions. So things that are binary, just two elements, those are going to have hydrogen in front, followed by a nonmetal, like chlorine. For example, in HCl. Then we have oxyacids. Those will still have hydrogen in them, again in the front, and then followed by an oxyanion. Like NO3, nitrate. And that acid formula would be HNO3. Again, H in front means that it's an acid. For naming binary acids, these are arguably easier. There's fewer steps. Our big signature piece for binary acids is, of course, having only two elements. And in the name, we put hydro in front. Hydro is important. The hydro in front means that it's binary. That's a signal word for chemists that it's just two things. We have some names for binary acids and oxyacids where if we don't have that hydro in front, the names are exactly the same. So the hydro lets us distinguish between those instances. So the hydro is the big part. Then we'll have the base of the anion name, and we change the ending to ic acid. So HCl, we've got just two things. It's a binary acid, so we add hydro in front. The base for chlorine is chlor. Right, just chop off the ene, change the ending to ic, and add acid to the end. The acid at the end, of course, also a pretty big giveaway that we're dealing with an acid. For HBr, we've just got two things. So we have the hydro prefix, indicating that it's a binary acid. The base for bromine, which is brom, change the ending to ic, acid, hydrobromic acid. Questions so far about acids? All right, two binary acids. I'll give you a shot at naming both of them. So we've got HF and H2SE. Just a note about the H2SE. You don't have to specify that there's two hydrogens. All right, HF. HF is a binary acid. A couple giveaways that it's binary acid. The top of the page says naming binary acids. Also, there's only two things. There's an H in front. That means it's an acid. We need to start our name off with hydro. We do that for every binary acid. And then we need the base of F. F is fluorine, so hydrofluor, not hydroflower. Hydrofluor, and we change the ending to ic and add acid. So hydrofluoric acid, as made popular in season 1 of Breaking Bad. Great for dissolving bathtubs. We also have H2SE. H2SE is also a binary acid. We only have two elements. We've got hydrogen and selenium. The H in front, again, indicating that we have an acid. So we're going to use our starting prefix, hydro, since we have a binary acid. Se is selenium. So the base for that is selen, and change the ending to ic acid, hydroselenic acid. Questions about those? Yes?
Since there's a 2 on the H or H, does that matter?
So the way that we figure out, if we were given a name, the way that we work backwards from the name to the formula is we would look at the base. So let's say that we had let's say we have hydroarsenic acid, if that exists. We have a hydro in front. This indicates to us it's binary. We also have this arsen part. Note that it's En, not On. We're not lighting fires. This is poisoning, because arsenic is bad for you. So arsen, meaning that we would have arsenic as our element. We would find arsenic, As, on our periodic table. It's in the 15 or 5A. That would form a 3- charge. Or we would expect it to be As3-. Hydrogen is in our group 1. That's going to be a 1+ charge. And so we would just do a crisscross. To get these to balance out. So we would end up with H3As. So all that the 2 here means is that we need 2 of those H pluses to balance out the charge on selenium, since selenium forms a 2- charge normally. That's why we don't have to specify. All right, now on to everyone's favorite, oxyacids. So we're combining all of the fun that we had with the hypo, per, 8-ite, all of that sort of fun stuff. And we're now making new things out of those. So our oxyacids contain oxyanions, things that end in 8 or ite in their names. They're all found in that top section of the green sheet. So HNO3 contains NO3, the nitrate, NO3- ion. H2SO3 contains the SO3 2- ion. Notice that this 2- charge corresponds to 2 hydrogens up front. Just however many hydrogens we need to balance out the charge. So we're just going to add H+ to balance the oxyanion charge, as it says at the bottom. H2SO3, since it's SO3 and SO4 is our base name 8 ending, that's sulfite. It's one fewer oxygens. And SO4 2- is the 8 form. So the first step for identifying and naming an oxy acid is figuring out we've got an oxyanion in there, and then we need to hunt down and work out the name of our oxyanion. We've got 2 rules for oxyacids. They are 8 turns into ic and add acid. And we've got ite turns into us and add acid since it's an acid. So 8 ic, ite to us. 8 to ic, ite to us. There is no change to per or hypo prefixes. Those just stay on there as is. So as long as you remember the 8 ic, ite us, you don't change the prefixes, the oxyacid stuff is really not that complicated. Figuring out what oxyacid you have is probably the hardest part of the process. So let's name some oxyacids. There's lots and lots and lots of options. The first one, let's name HNO3. So we've got an H in front. That means it's an acid. However, we have more than 2 elements. That's a sign for this class that we've got an oxyacid. So our oxyanion is NO3. We could work out that it has a 1- charge. We would find NO3 with whatever charge it has on our green sheet and discover it's nitrate. So we've got our base name for our oxyacid. It's the niter part. So we're chopping off that 8. And then we remember 8 turns into ic and add acid. So this is nitric acid. Eight to ic. Question?
There's no hydro prefix?
There is not a hydro prefix. Hydro is only for binary acids. And then for H2SO3, again, we've got H in front. That indicates to us that we're working with an acid. And we can find the oxyanion, SO3. We would find SO4 2- on our green sheet. That is sulfate. We have 1 fewer oxygen. We have SO3. So SO3, still 2-, is sulfite. So now we've got the name for our oxyanion, sulfite. So we can name this sulf. What does our ite ending turn into? Us, O-U-S. And there's this fun little trick that we do here. We add in a UR because of course. So this is sulfurous acid. So it's, in this case, it's really the base of sulfur, but it's the whole thing. If you put sulfic or sulfous acid, I'll understand what you mean. I don't expect you to get it perfect, but ideally you would put in sulfurous acid Phosphorus also has a similar thing. Which might be coming up here. It's not. Perfect. Okay, some for you to try. HNO2 and HClO4. I'll give you a couple minutes to parse those out. All right, HNO2. We can tell that it's an acid because it has H in front. We can tell that there's more than two elements because we've got more than two capital letters. So we need to find something that looks like NO2, since that's an oxyanion. Something that looks like NO2 is NO3-, which is nitrate. However, we'll notice that that's not exactly the same. We have NO2, not NO3. How do we change the name to adapt to having one fewer oxygens? Yeah, we put an ITE at the ending. So for NO2-, it's nitrite as our oxyanion. So we've got niter. And how do we change the ite ending? What do we turn that into? Us, ite to us, so nitrous acid. We go through a similar process for HClO4. The H in front means we have an acid. We identify that we've got an oxyanion. And we find something that looks like it. Let me scooch this down. So ClO3- looks an awful lot like ClO4. ClO3-, if I'm not mistaken, chlorate. Instead of removing an oxygen, we've added an oxygen. Right, so we have ClO4, still a 1 minus. What do we do to adapt to adding 1 oxygen? We perchlorate. To make the name, we have to change the ending to make it an acid. So perchlor. How do we change the ending for 8? I don't think it's that gross. Perchloric acid, 8 to ic. The jokes may be dumb, but they are free. So perchloric acid. Questions about oxyacids? So those are our nomenclature categories. Here's one version of a nomenclature flowchart that you might use to parse out how we're going to name stuff. We have 3 main categories of things. We've got ionic compounds. Ionic compounds are a metal and a nonmetal, or multiple nonmetals. We've got covalent compounds, things that form molecules. These are only nonmetals. In this class, it's just 2, just binary molecular compounds, nice and easy. And then last but not least, we've got acids, things that have H in front. So this is the first step in our choose your own adventure, or follow my adventure rather, flowchart. Identifying what the kind of thing is using one of those 3 categories. It will only fit into one of those categories in this class. If we have a metal and a nonmetal, that's of course an ionic compound, and so we have to do a couple of things. We have to name the cation, figure out what the cation is, and I think this is supposed to say anion last. We are not going to use prefixes. Prefixes don't show up here. If we have a binary, we will either have a monoatomic ion sodium is always Na+, so we don't specify charge. If we have something from our transition metals that isn't zinc or silver, like iron, Fe, iron has options. So we have to specify the charge. For example, IV or II or some other thing like that within some Roman numerals and parentheses. And then our monoatomic anion is going to have the ending changed to "ide." We also have polyatomic ions. Polyatomic ions in this class typically being oxyanions. If we have an oxyanion, it's just the name of the oxyanion. We don't have to change the ending to "ide" or something. So polyatomic ions, these will often end in "ite" or "ate." Our binary ones will end in "ide," with some minor exceptions. So there's lots and lots of possible options there. For our molecular compounds, we read them as they lie. So we're going to have 2 things, a first element, a second element, and we give them prefixes. Prefixes are the thing that's unique to molecular compounds, covalent compounds. So for example, CO2, we omit the mono in front. We add di, since we have 2 oxygens, so dioxide. And then we just talked about our acids. Acids always have that H in the front. That's how we know they're an acid. And for our things that are from oxyanions, ite turns into ic, and ate ending turns into ous. If we've just got 2 things, if we've got a binary, then we have hydro in front. We will have a worksheet where you get to practice doing nomenclature. That's scheduled for during one of our labs. Questions right now about any of the nomenclature stuff? So here's an example of where we could run into trouble with our acids. HCl, HClO3. Please don't pack up yet, we still have more. So HClO3, ClO3 is chlorate. This is chloric acid. HCl is also chlorine for the base. Change the ending to ic, add acid at the end. If we don't add the hydro prefix, we could confuse these 2 things. And that can happen for several of our possible acid combinations. So this is why it's important that we have that hydro part, is so that you can work backwards from hydrochloric acid to figure out that it's binary, or you can work back from chloric acid without that hydro prefix to figure out that it's an oxyacid. All right, last slide, more practice stuff for you to do. Combining all of our nomenclature knowledge together, please attempt to name the following chemicals. So all of this nomenclature stuff, if you have somebody that you're friends with in the class or who's taken chemistry before, this would be pretty easy stuff for you to practice a back and forth, like make it a shootout game basically. One of you comes up with a formula or produces a name and then give it to the other person, see if they get it. And then they do the same thing for you. And if there's a dispute, you ask Google, because Google will probably give you the right answer. So that would be one way that you could practice your nomenclature to sort of build up your fluency. All right, our first one, PCl3. We have a binary molecular compound. Our first one is phosphorus. We omit the mono. And then we have a prefix, tri for 3, and then chlor for the base of chlorine. Change the ending to IDE. For HClO3, we have an acid in the front, so of course we're going to have acid in the back of our name. We don't have just two things. It's not a binary. We've got ourselves an oxyanion. ClO3 minus is chlorate. We've subtracted 2 oxygens off of that, so we would change the ending to ite, and then we would add that hypo prefix on the front. And so our name here is hypo, the base chlor. Change the ite ending to OUS, hypochlorous acid. In C, we have an ionic compound. Calcium is a metal. And we've got OH. OH is one of our polyatomic anions. You can find that on the bottom of your green sheet. So the first thing we want to do is name the metal. Calcium always forms the same charge. It's a calcium 2+ ion when it's an ion. And we have hydroxide, so calcium hydroxide. We don't have to specify how many hydroxides we have because hydroxide also is always a 1- charge, so we could work backwards. For D, we still have a metal up front. Nickel is a metal. Nickel can form multiple charge options, so we would have to figure out what that charge is. So it might be helpful, since we've got an oxyanion, figure out what the charge of our oxyanion is. PO43 minus is phosphate. So PO43 minus is our phosphate. We've got 2 of those, total of a 6- charge. So our nickel, between the 3 of them, has to have a total of 6 positive charge. So they're each going to have a charge of 2. So nickel, 2, phosphate. And then our last one is an acid. It's a binary acid, so we're going to have that hydro prefix, the base name of fluorine, fluor, change the ending to ic, and add acid, hydrofluoric acid. Questions about any of those? Okay, that'll do it for Chapter 3.